Hello, my name is Hassan Mahach. This presentation is about the thermal performance of an air-to-air heat exchanger connected to a single family house for air heating and cooling under European climates. The presentation outline is as follows. The air-to-air exchanger uses the underground soil as a heat source or sink to heat or cool the outside air that will be blown into the building. This operation is possible thanks to the high thermal energy of the soil, leading to a nearly constant underground temperature at a certain depth over the year. This temperature, which is almost equal the yearly average air temperature of the location, is of course higher in winter and lower in summer than the outside air temperature. To take advantage of this, the air-to-air exchanger consists of buried pipes in which the outside air is pushed down to be heated or cooled through the contact with the ground. The considered building is a reference European house named SFH 45 according to its heat load, which is approximately 45 kilowatt hour per meter square per year in the context of Strasbourg climate in France. The total volume and net floor area are 390 meter cube and 140 meter square respectively. The building was developed by the International Energy Agency in the frame of the solar heating and cooling program for the comparison of different systems. The elements of this building are constructed to represent a renovated building with a good thermal quality of the building envelope. The parameter of the air-to-air exchanger, as well as the thermophysical properties of the soil, the outside air, and the PVC pipes are summarized in these tables. These parameters were deduced from a recent parametric study considering all the parameters of the air-to-air exchanger. Regarding the conditions of the simulation, this study was conducted in the context of two European climates, which are Strasbourg and Athens. The thermal behavior of SFH 45 building connected to the air-to-air heat exchanger is modeled using TRNSYS software, using two main models, which are type 56 for the building and type 460 for the air-to-air exchanger. The building is simulated as one thermal zones. The air-to-air exchanger should supply a ventilation airflow rate of 0.4 air change per hour. The dynamic simulations were conducted for 2 consecutive years, where the first one is only for the soil thermal conditioning. The temperature and the humidity of the air at the inlet of the air-to-air exchanger are assumed equal to those of the outdoor air, and the air-to-air exchanger is operated only when the temperature at the outlet of the air-to-air exchanger is higher or lower than the outdoor air temperature in heating or cooling mode. These two figures shows time variation over 1 year of the air temperature at the air-to-air exchanger inlet and outlet. These figures shows that in the Strasbourg climate, the air temperature at the air-to-air exchanger outlet vary between 8 and 15 degrees C, while it vary between -10 and 32 degrees C at his inlet. And in Athens climate, the air temperature at the air-to-air exchanger outlet vary between 90 and 27 degrees C, while it vary between 0 and 37 degrees C at his inlet. The result of this study shows that using a set point of 20 degrees C, the air-to-air exchanger can reduce the ambient heat load from 46 to 55 from 46 to 25 kilowatt hour per meter square per year in Strasbourg climate, and from 7 to 1 kilowatt hour per meter square per year in Athens climate. Regarding the summer season, the result shows that the air-to-air exchanger can reduce the ambient cooling load from 7 kilowatt hours per meter square per year to 2 kilowatt hour per meter square per year in Strasbourg climate, and from 29 kilowatt hour per meter square per year to 26 kilowatt hour per meter square per year in Athens climate.